Hello, this is our UC Merced Racoon Movement project for Math 150 Mathematical Modeling for Spring 2021. So our team members consist of Jairo, Carl, Brianne, and Tommy, and our mentor was Camille Carvalho. We could go ahead and move on to the notebook itself. So an understanding of animals and its relation with the environment can help provide valuable information for many studies. These studies include disease prevention or information on endangered species, more specifically animal movement. Animal movement helps understand behaviors such as habitat selection, mating, and also understand responses to the environment changes. Raccoons are the most distributed species of the New World family Pro Procyonidae, meaning that they inhabit wide ranges of environment throughout the United States, especially Central California. Raccoons are very adaptable and their movement patterns and social interactions vary with unique factors, including climate, habitat, and human activity within that area. Most studies of raccoons are under the environment of shallow flooded forest areas, but UC Merced is a fairly new school located on hot, dry land with not too much research on wildlife activity. There are many raccoon sightings ever since the beginning of its development. And since raccoons are very adaptable, they might develop a way to coexist with UC students. Their behaviors from other raccoons might positively or negatively impact students. In this project, we investigate the movement patterns of raccoons depending on where they are on campus. We will use the random walker model and concepts to illustrate the movement patterns with groups of raccoons in a specific area and how likely they will move accordingly to where they are located on campus. Random walkers is a mathematical abstract concept known as a stochastic process that describes a path that consists of succession of random steps on some mathematical space. Knowing these behaviors and movement patterns will give a better understanding on where to go and not to go on campus. Although the reality of everything is not random, this model helps approximate movement patterns. In the upcoming sections, we present our code of random walkers, numerical and analytical results, and our final thoughts towards the random walker models.
So starting with our code, we imported three libraries, NumPy, PyPlot, and Camera. NumPy is used to create arrays. Plotly is provided online graphing, analytics, and statistical tools. And Camera will create animations which we'll be utilizing at the end of our code. Then we created some variables. We created 5 variables, A, which equals the radius of the environment, and the number of iterations, number of walkers, which equals number of random walkers or raccoons, dx, which is equal to the length of each step in the x direction, and dy, which equals the length of each step in the y direction. As you can see here, these are the two arrays that we have for the x and y direction. The first number indicates the random walker that's going through the motion, and the number 3 indicates no the number 0 indicates the iteration of the steps, and the number 3 indicates the random walker. For the x direction, the y same thing. The 3 indicates the iteration, and the 5 indicates the specific random walker. And by using the random.uniform function, we can initialize both x and y arrays for the iteration for each of the random walkers with the random values that is within one of the 4 areas in the environment. And those 4 areas are within UC Merced, which are the Summit dorms, Terraces dorms, Pavilion area, and Bellevue lot.
The initial conditions chosen for A was one large enough to represent the lower half of campus. The other variables, such as n for time step and the number of walkers, were chosen as 100 and 500 respectively, as we felt they were reasonable sizes to demonstrate the model. And the generated walkers were divided into 4 groups to show the behavior of raccoon movement on different sections of the map.
Here we created an array that takes in an array with 4 values. The first 2 values are the dimensions on the x direction of a box in our environment, and the last 2 values are the dimensions of the box in the y direction. And this will be used once we create the movement and we create the animation.
Each area within box represents a building or a body of water that impedes Racoon movement.
Here we have our first function, which basically maps the the boxes in the map in our environment. And here our second function, which is called fill map, draws in or fills in the boxes in our environment with the color chosen. Here we create another uh, array that takes in arrays of 4 values, and this array is called area, which basically takes in the first 2 values are the x direction and the last 2 values are the y directions of the box. And but however, these are attraction boxes for the raccoons, so basically a bias in our code.
These bias areas are placed around the dining centers, as well as an existence of a larger one on the lower half of the map to lead Racoon movement towards the dining centers.
This function called box constraint movement basically takes in the current location and the last location of a random walker, and then takes in the boxes array and compares them and makes sure that the random walker is not inside the limits of each box inside the boxes array. And if one of the raccoons are, then the this function will make it so that the the random walker current location becomes their last location, which is outside the box. And in here, uh, this function area constraint movement takes in the previous x and y position of each random walker and a list which indicates the traction area of the environment. This function compares the last location of the random walker to the traction area. And if the random walker is within that area, it will change the probability of the movement accordingly.
The probabilities chosen here were chosen such that Racoon movement is slightly skewed towards the dining centers when within the area, and when outside of the area, the Racoon movement stays equal chance.
Here, we make a for loop in order to iterate through all the steps taken by the random walkers. Inside the for loop, we create an array sized the amount of random walkers called S containing random numbers between 0 and 1. With the values located at S, we determine if the random walker will move left, right, and down and up. Then we have another for loop to iterate through all the random walkers. In here, we call the function area constraint movement and store the results into a variable called move. Next, we have a series of if and else statements which compare the values of the S and the move arrays. Inside the if statement, the random walkers both X and Y location will increase and decrease. Finally, we have the function box constraint movement to check if any of the random walkers are in the restricted area.
This map right here prints out the initial starting points of the random walkers, which clearly shows that the random walkers are starting in 4 distinct locations. The following map is a map of the random walker's movement across the time steps. So we can see where the raccoons would want to move in general. As we can see here, there are large white areas between the random walkers, showing that the raccoons indeed are not going through the buildings. And we can also see that the raccoon movement seems to be slightly skewed upwards despite a generally uniform movement. This suggests that the raccoon movement overall is slightly skewed upwards with a mostly uniform movement.
By importing the library interact, we are able to create an interactive environment which lets us see each step of our random walkers in an animation. By creating a function called interact walker, which will go through all the random walker steps. Also, by using the library plotly, we create an environment 10 by 10 size, which the random walker will not be able to go beyond thanks to the functions setXlim and setYlim, provided by plotly. Next, we had two different for loops, one iterating through the box's arrays and the other one iterating through the array. In both of them, they call the function box constraint map in order to draw the buildings in the environment and the attraction area for the raccoons respectively. Finally, we use the scatter plotly function to plot all the random walkers and use the fill map function to fill in the buildings with their colors.
This section of the code is the actual model in itself. As you can see that it's the map, it's a little map of the campus that shows the raccoon movement leading towards the dining centers. Gyro, can you show the example?
Yes.
As we can see here, the overall movement of the raccoons does seem mostly uniform. There seems to be a slight bias moving upwards, especially towards the lower half of the map, which makes sense as that's how we left the areas of bias. It suggests that the overall governing equation is a diffusion advection equation with slight upward movement. This will be explained further within the analytical results. The model does a great job depicting raccoon behavior within the search for food. However, the model can be improved in many ways, many of which we have considered, but were unable to implement within the scope of this project. Things include a possible predator, the speed in which raccoon moves, amongst other things.
Okay, so as was like previously discussed, each raccoon around the marker has a possibility of moving like either up, down, left, or right. And then for the majority of the map, so like basically all areas outside the areas of bias, which was shown like in the model as red rectangles, the raccoons have like an equal probability to go in each of the four directions. So like a 1/4 probability to go right, up, down, and left. So first we wanted to find an equation that can describe the motion of the raccoons for like most of the part of our model, like when they're not in the areas of bias. So to do so, we can let C of X, Y, and T be the expectation of the number of walkers to be in the window delta X, delta Y at time T. So this means that C of X, Y, and then T plus delta T are like the expectation at T plus delta T will be equal to the expected number of walkers coming from the left, the right, up, and down. So that's shown as like that very first equation. So then after that, we did some algebraic manipulation of the equations. And then we see at the end that there's like a second order central difference for both X and Y, and which gives like the second partial derivatives of C with respect to X and Y. And then once we do that, we see that this final equation right here is the heat equation. So what we found was that the movement of the raccoons like diffuse like heat, and like they follow the heat equation in our model if they are outside the areas of bias. And then, however, the heat equation can't be used to describe the motion of the raccoons. But like our entire model, like as was discussed, we have areas of bias in our model, where the probability of a raccoon going in each direction is no longer 0.25. And once we take these areas of bias into account, we saw that there's a slight bias for the raccoons to move up rather than down in our model. And we estimated this to be this bias to be like a 0.25 probability to move left, a 0.25 probability to move right, 0.3 to move up, and 0.2 to move down. So we wanted to find an equation now that takes into account this bias to move up rather than down. And so like following like similar steps like previously, we can let C of X, Y, and T be the expectation of the walkers to be in the window delta X, delta Y at time T. So what this means is the C of X, Y, and then T plus delta T will be equal to the expected number of walkers coming from the left, right, down, and up. So that can be seen like on that very like top line. So that's the equation. And then again, we did like some manipulation of the equation. And then at the very end, we see that this like first and second order central differences with like respect to like X, and then like the second one with respect to Y. So then once we do that, we see that we get this equation at the very bottom, and we can recognize that as the advection diffusion equation. So overall, what we found is like for the majority of the map, like the areas outside of like the biased areas, the raccoon movement can be like described by the heat equation. And then once we added the areas of bias, the movement like can be described by the advection diffusion equation.